Hi, everyone. I'm very glad that we got the opportunity to have another edition of Transformer at Work in person. Today, I'm going to talk about the research that we have been doing at Zeta Alpha, and it has been focused on neural search. Great. I think I'm going to just go with this one. Yeah, it has been focused on neural search, so I'm going to tell you about the exciting work that we have been doing. Great. So what is neural search? Neural search is an instance of semantic search. And the general idea is that we have queries, we have documents. If we can map them to an embedding space with some sort of representation learning, and they all live in the same embedding space, and then we can do search by doing nearest neighbor findings. So given a query, then we can find the most relevant documents for that query. Let's give it another try. Cool. OK, it's not. Yeah. Great. So the question is, why using neural search? So the main reason is that it fills the gap between traditional search and some of the missing challenges that exist there. So one of the main ones is the lexical gap that we have. So we go beyond trying to match a surface form of words in the query to the document. So we go to the underlying meanings of the queries and of the documents to do the matching and the mapping. And also another good reason to do neural search is to have a better understanding of contextual and complex queries. So queries that are just like questions or long sentences. It's not about the keywords anymore, but it's about the relations between the words. So if we have a good representation for that, the search result would be much better with a neural model. Right, so there are two different ways of doing neural search. So there's a one-stage pipeline and two-stage pipeline. So in the one-stage pipeline, we have a collection of documents. We have a query coming in from the user. We do some sort of retrieval, neural or traditional. We get the top K results of the documents for that search. We can also do two-stage retrieval. So after getting the results for the first stage, we can have another re-ranker on top of that. So the input of the re-ranker is not the whole collection of documents anymore, but it's the results of the search. So the top K documents are much smaller, so we have the opportunity to do more complex things there. And the idea is to reorder these documents to get, hopefully, to a better order of documents that are relevant for the user query. Right, so what did we do in the last year? That's the main topic of my talk. So one thing that I've been working on for the past couple of months was training a model to understand basic laws of physics. So that's my baby. It's not, and he's a fan of Bayesian probability so far. But it wasn't all that I've been working on. So there were other projects, maybe not as cute, but definitely as exciting, that I was working on last year with some really smart people at the research team in Zeta Alpha. So here are the 4 papers that I'm going to very briefly go through today. And I do want to mention, so they are available online. The data, the models, the code is also available online, so I encourage everyone to check them out. But what are the questions that we wanted to answer in different research projects that we were working on? So you can argue that the quality of a system, so in this case a neural search system, can be a function of a number of features. So one is the data, the other is a model, and the other is hyperparameters. And in each of these features, there are different challenges, there are different optimizations that you can do, different changes that you can make. So we were coming up with basically a bunch of questions listed here, and we were working on that in different projects that I'm going to go through one by one. So the first research question that we wanted to investigate was, how can we adapt neural retrieval models to new domains? I think it's pretty much, no one is going to argue with that if you say neural models, they are data hungry. So the more data that you have and the more diverse data that you have, the more appropriate in-domain data that you have, the better your learning will be. And it's not always the case. So if you are working in a particular domain, in a particular language, you might not always have enough data. So there are several ways of dealing with that. So there has been some works in the last year using large language models, for instance, at inference time or at fine-tuning time to basically deal with this problem. So what we were actually asking here was, okay, these large language models, they're expensive, both money-wise, time-wise, everything. So is there a way that we can use them in an efficient way so that we basically address this domain-specific neural search problem? And we found out that, we had this idea of doing data augmentation with these large language models. So with a good prompt, we can ask these models to generate synthetic data that we are missing to train our models. So rather than using these language models at training inference time directly, we use them to generate the data. Right, so here's the pipeline for this idea. So there's a blue box, so there's a prompt. I'm going to explain a bit more about that later. We feed that into a large language model and ask the model to generate a question for a given document. So then we have pairs of document and questions, and the probability of generating those questions. And we do that multiple times, and then based on the probability of the queries that we get, we pick our training pairs to train our re-ranker. Right, so I talked about the prompt. We experimented with two different ideas about how to do this prompt-based generation. So one was we call it the vanilla or simple prompt, where we give the language model 3 examples, so 3 document question pairs from our own data set. So it can be from like in-domain data that we have. And then as a 4th example, we give a new document every time, a new document that we don't have a query for, and ask the model to generate the query. So in the second set of experiments, we came up with a more interesting, I would say, prompt. So what we had in mind here was that what if we tell the language model what we consider is not a good question and force it or urge it to generate a better question. So we use the original questions from the training data as examples of a bad question. And then we provided a good example. So you would ask, like, what would we define a good question? So in this scenario, our idea was a good question is a question that is more descriptive and more complex. So in order to answer that, you need to know more of the document. So the answer is not just like one word in one sentence in the document, but rather you need to basically understand the document to answer that. So again, a few shot scenario. 3 examples. So here, for instance, you see like the bad query is how large is the Canadian military from the MS Marco data. The good question is information on the Canadian armed forces size and history. So asking a bit more from the language model and then generating questions. Right, so here is a table. So in this talk, I'm going to show a couple of tables. But I don't want to go too much into details of them. But what I like to mention here is that our proposed approach, especially our more complex good, bad prompt approach, got improvements on, and we are evaluating on the Beer benchmark, which Sergi talked about, so the zero-shot evaluation. And we got improvements all over the place. So better than BM25, better than existing baselines, the recent OpenAI paper, the CPT text one, with much smaller size models. So it's both efficient, performance-wise, and cost-wise, so it's really nice. Right, so the second work that I want to talk about is we were looking into this question, how to train a multi-purpose retriever. So far I talked about queries and documents, and mostly I was talking about short queries or like phrasal queries or like questions at most. But we can also have long queries, right? So we can also try to do like document-to-document search. And the question that we wanted to investigate here was, is there one single representation, one single model that can work relatively well in both scenarios, with short queries, but also with long queries? So for this work, what we did was to do multi-objective representation learning. And the main idea was we have different data sets with different objectives. And by the way, so the domain of this work was scholar document retrieval. So the data sets that we have, it can be like the general domain MS Marco, which is like a question answering data set, a supervised data set. But we can also generate and create data sets in the particular task that we wanted in an unsupervised or semi-supervised manner. So that's exactly what we did. We generated the citation graph from like context and how documents cite each other, and also the independent cropping, which is an unsupervised way of creating basically pairs of queries and documents. And these two were in domain. So then the question is how to mix them, because we want to learn from all of them. We don't want to forget information from one of them when we fine-tune on the next. But they are also like very different in terms of structure, objective, everything, right? So we opted for 3 different ways of combining these. One was in-batch mixing, where in each batch during training, we basically can have documents, positive and negatives from any of these data sets, and it's a weighted random sampling. The other is the alternate batch mixing, where the trained data is equally selected from each of these 3 data sets, and in each batch, there is no mixing between data sets, so you can imagine that the negatives in the batch are more relevant for the positives. And then there's a fine-tuning, where we train on one of these and then fine-tune on another one. So here are the results for this work. We have the Beer subset of data sets here, which is mostly short queries. We also have the iClear 2022 data set here, which is a document-to-document search. So queries are much larger. And we do see that indeed by a deliberate mixing of these objectives, we can have a model that works well on different types of queries and different types of data. Right, now to the third research question. So what we were wondering here was, OK, we have these dense retrievers, we have the re-rankers, they are really nice, but how are they really good at generalization? And another question that we were also wondering was, so there are like really large models, there are really small models that are distilled, which they are basically learned to mimic the probability distribution of a larger model. But when we are working in practice with these models, which one should we pick? Which one is a good choice? And in this work, what we tried to answer were basically these questions. So we had some really interesting findings. So here you see, so on the top, when we are evaluating in domain. So when evaluating an in domain evaluation set, we saw that size doesn't matter so much. So For instance, the mini-LM re-ranker on the top is like a much smaller model that is distinct from a much larger model. It's performing almost as well as the Mono T5 model, which is a number of times larger than that one. So when we are working in domain, the difference is really small when we increase the number of parameters. But the trend is actually different when we evaluate out of domain. So the same models, when we evaluate out of domain, we see that, yeah, number of parameters does matter. So smaller model, they're not bad, but just by increasing the sizes of the model, we see improvements in the performance. And this is a signal that the number of parameters, there is a correlation between that and a model being able to generalize to out-of-domain tasks. There was also a really cool thing that happened in this work, and that was that with our re-ranker, with the large one, with the 3 billion parameter one, we achieved state-of-the-art results on the beer benchmark on most data sets, I think 13 out of 18. Yeah, that was also a nice finding. And lastly, I want to talk about non-English cases. So far we talked about retrieval, the problem of data, but it was all about English search. But once we move to non-English domain, then it's even worse. So the size of the data is really bad. Usually the diversity of the data. So we were wondering how we can solve this issue. The idea that we had was, okay, there is this MS Marco. There's this MS Marco data set that's really nice. It's general purpose. It's really large. And it can be said that it's like the backbone of every neural retrieval research. So it's like really useful in this field. But it would be really cool if we can have a multilingual version of this data set. So yeah, you can either manually translate millions of query document pairs into tens or hundreds of languages, but you can also use automatic translation. So yeah, much more cost-effective, and that's what we did. So the idea here was to see if we generate the multilingual version of MS Marco automatically using neural machine translation, can we still use these models, these data sets in each languages to learn reasonable retrieval models for each languages or not? Yeah, right. And yeah, that's what we did here. So we picked 13 languages. Yeah, a lot of, so the languages were picked by the number of Wikipedia articles and number of people that speak that language. So hopefully, it like a good starting point for translation, but definitely not where we should stop. And then we generated the M-Marco data, so the multilingual MS Marco data. And we also benchmark the existing, the BM25 retrieval and also neural retrieval on each of these data sets. So I think it's a really cool data set if you are working on multilingual data, or like there's the Dutch language there. If in your case you are working on Dutch retrieval, give it a try and check it out. One last thing that I want to mention is that in this work, we also were wondering if there is so we have the translation generated automatically, right? And we wanted to see if there's a correlation between the quality of the translations and the quality of the retrieval system that we generate later. And we saw that, yeah, indeed, there is a weak correlation. So it is also more or less expected, right? If we improve the quality of translations or improve the quality of the data set that we create, we can also see improvements in the retrieval performance. Right, so takeaways. I know that I probably talked about a lot of different information in this talk. So there were 4 different papers, and I do encourage you to check them out to know more about them. But I do want to summarize our findings in these works here with a couple of statements. So one is that we saw that prompt-based synthetic data generation is promising. We also saw that generating multilingual search data sets is also effective. So what this tells us is basically if you compare having no data with generating some sort of noisy data, you might expect that, okay, the data should be really too perfect to use to train these models. But we found out that noisy data is better than no data, basically. So if you are dealing with lack of data, try to go with some sort of automatic way of data augmentation and generate some sort of data that is going to be noisy, because it is. But it can help in the current state when you have no data. We also found out that in-domain effectiveness is not a good indicator of zero-shot effectiveness. And also, when we generalize to new domains, re-rankers are better than dense retrievers. So I do also want to point out here that a lot of us, also maybe at a lot of companies, you might want to use models out of the box, that models that perform state-of-the-art on a particular data set that comes out new and shiny. But take this into account. So what that model was trained on, what is your domain, whether it transfers, the quality transfers to you or not, it's not always the case. And so, for instance, we found out that re-rankers are better in generalization than dense retrievers. So that's a good starting point to know when you want to use existing data. And that's it. Thank you for your attention.
All right, we have time for a couple of questions, maybe. Does anyone have a question? I might ask you to move a little bit to the front, because...
No.
Oops.
Not too much.
Hi.
Hi.
Great talk. Thanks. I just had a question about prompt engineering, actually, because just yesterday in a newsletter, I read that some startup is now, they specialize in making new prompts. Mm-hmm. And I was wondering that the only reason that came into business is because giving the right prompts to the model is challenging. So I was just thinking about how time-consuming / effective it's going to be, because sometimes the domains can be simple, but not always. For example, if I really think about scientific articles or data that you would need there, I don't really see prompts working. So would you just call this as trivial, or is it very domain-dependent, etc.?
Yeah, that's a good question. So we have a Fernando here that had some ideas about prompt engineering startup a while back. So it's good to hear that it's already picked up. Yeah, I think so. We are trying to stay, with these models and the learning process, we are trying to stay as objective as possible, not get involved, right? But with prompts, it's inevitable that you are putting your priors and your biases in how you create the prompts, you as a human being, the researcher that you do. So from my experience, it takes some time to find what's working and what's not working. So it is also these models, they are a lot prone to a small change in the prompt, just capitalization of one word can change the whole output. Just realizing these nuances and playing around with them, I can see that it might require some experience and expertise. But I do hope that prompt engineering doesn't stay where it is, where some people would try to find the best prompt. So I think that the main direction of going forward should be how we can also automate this phase, and also automate in sense of like learning from data or like the task that we want to solve, rather than trying to have someone who is like really an expert to how to generate their prompts. I do also have to say that it's not always easy. So for our experiments, we actually, these 2 prompts that I showed, they were the first prompts that we used and the first examples that we used. So we didn't really try browsing and see what else we can do, and we didn't want to do that either.